A matrix can have eigenvalues that are real and distinct, real and repeated, or complex. We'll look at the real and repeated case later, but for now we're going to look at complex eigenvalues. If lambda equals alpha plus beta I and lambda bar equals alpha minus beta I, that alpha bar is the complex conjugate, then we've got two solutions to a differential equation, one of which is x equals ke to the lambda t, and the other is x equals k bar e to the lambda bar t. As we've seen before, we can represent this exponential with the imaginary exponent as a complex number using sine and cosine. So ke to the lambda t is ke to the alpha plus beta I t. K, remember, is a column vector of constants. E to the alpha t is a real valued function. But then for the beta I t part, we've got cosine beta t plus I times the sine of beta t. Considering the complex conjugate of lambda, the things that change are that k becomes k bar, the conjugate. We have a minus in front of beta I, which gives us a minus in front of the sine term. By the superposition principle, if we multiply existing solutions by constants and then add them together, we still have a solution. We're going to choose strategic constants to put in front of these solutions. We're going to say that x1 is equal to 1/2 of ke to the lambda t plus k bar e to the lambda bar t. So that's 1/2 times that whole thing. And that's going to give us e to the alpha t times 1/2 of k plus k bar cosine of beta t minus I over 2 times negative k plus k bar sine of beta t. For x2, we're going to use the superposition constants that give us I over 2 times negative ke to the lambda t plus k bar e to the lambda bar t. That'll give us e to the alpha t times the quantity of I over 2 times negative k plus k bar, all that times cosine beta t, plus 1/2 k plus k bar sine beta t. This is all going to really clean up in just a bit. How does it clean up? Okay, as an aside here, if we take 1/2 of lambda plus lambda bar, just a complex number and its complex conjugate, that is 1/2 of alpha plus beta I plus alpha minus beta I. The imaginary part subtracts out. 2 alpha over 2 just gives us alpha. I over 2 times negative lambda plus lambda bar is going to be I over 2 times negative alpha minus beta I plus alpha minus beta I. And this time the alpha subtracts out. And simplifying the betas and the i's, we end up with just the beta. The alpha is what we call the real part of the complex number, lambda, and beta is the imaginary part of lambda. You'll notice that this lambda plus lambda bar is showing up in the form of k plus k bar, and negative lambda plus lambda bar is showing up in the form of negative k plus k bar. I said before that k was a column vector of constants. I forgot to mention that those constants are complex, and that's why we can talk about k bar. So out of all this stuff that we just looked at, we have a couple of expressions involving k that I'd like to focus on. Let B1, uppercase B1, it's a vector, be what happens when we take 1/2 of k plus k bar. And let B2 be the I over 2 negative k plus k bar. Then x1, as written above, is going to be e to the alpha t times b1 cosine beta t minus b2, these are both vectors, times the sine of beta t. And x2 is e to the alpha t b2 cosine of beta t minus b1 times the sine of beta t. These are two linearly independent solutions, and they're all in terms of real numbers because of what we did with k and its conjugate. This leads to a theorem. Let lambda equal alpha plus I beta be an eigenvalue of A, and let B1 be the real part of the vector k and B2 be the imaginary part of the vector k. Then x1 is e to the alpha t times the quantity of b1 cosine beta t minus b2 sine beta t. x2 is e to the alpha t b2 cosine beta t plus b1 sine beta t. That's a bit to remember. You'll probably remember it just by using it a few times. And let's get into that. We're going to find the general solution of a system. Dx dt equals 4x plus 5y. dy dt equals negative 2x plus 6y. I'd like you to pause this video and go ahead and find the eigenvalues. We've got the determinant of a minus lambda I equals 0. That's going to give us, for multiplying upper left by lower right, lambda squared minus 10 lambda plus 24. And then subtracting negative 10 gives us plus 10 equals 0. Combining the 10 and 24 gives us 34. Subtracting that from both sides gives us lambda squared minus 10 lambda equals negative 34. Completing the square means adding 25 to both sides, ultimately to get lambda equals 5 plus or minus 3i. What a surprise! We have complex eigenvalues. When we have complex eigenvalues, I'm only ever going to use the one that has the plus in front of the imaginary part. So here I'll use 5 plus 3i. When we did what we did to find what b1 and b2 were, we actually did use both lambda t and lambda bar t in the exponent. We used both of the eigenvalues in order to generate the expressions that we're going to be using, or the solutions that we're going to be using. So the negative is built in. Really, it's built into the sine and cosine. Now, using lambda equals 5 plus 3i in the matrix A minus lambda I is going to give us 4 minus the quantity of 5 plus 3i, and then 5 as the top row, negative 2, and 6 minus the quantity of 5 plus 3i for the bottom row. And remember, it's that matrix times k equals 0 that gives us our k, or our eigenvector. One pitfall to watch out for is make sure we distribute the negative when we're simplifying inside of this matrix here. Doing so gives me negative 1 minus 3i, 5, and negative 2, 1 minus 3i, times k is equal to 0. And ordinarily what I would do is row reduce, but it gets a little tricky when we've got complex numbers. I mean, tricky isn't really a reason to avoid it, but remember that all this comes about because a determinant is equal to 0, and if we want to check this thing, we can compute the determinant of the matrix that's multiplying k. Negative of 1 plus 3i, I factor that negative out, times 1 minus 3i, minus negative 2 times 5 is actually going to give us negative 10 plus 10, that equals 0, and that tells me that the determinant is equal to 0, which means that one of these rows is actually a scalar multiple of the other row. To quickly check that, multiply the bottom row by 5 and multiply the top row by 1 minus 3i. Be careful with your arithmetic, and you'll see that they turn out to be the same. Since in our system both of these rows then represent the same equation or equivalent equations, we can pick one or the other and write down the equation that it represents. I'll use the second row. Negative 2k1 plus the quantity of 1 minus 3i times k2 is equal to 0. Now remember, we just need to pick values of k1 and k2 that satisfy this equation. Suppose we decide to solve for k2. I know it looks like kind of a weird choice, but if we did, then we would have that k2 is equal to 2 over 1 minus 3i times k1. And one of the easiest things that I can think of to do in a situation like this is to pick k1 in such a way that we clear the fraction. So why don't we let k1 equal 1 minus 3i? Then we get that k2 is equal to 2. And that gives us a vector k that has this top entry 1 minus 3i and the bottom entry 2. In the preceding conversation, we were looking at splitting this up into a b1 and a b2, where b1 was the real part, b2 was the imaginary part. So really what we want to do is split k up into the form of b1 plus b2i. That's going to look like 1, 2, that's our b1, plus negative 3, 0 times I. So b1 is equal to 1, 2, and b2 is equal to negative 3, 0. Using what we saw before, x of t is then equal to e to the 5t for the real part of lambda times b1, so 1, 2 times the cosine of beta t, where beta was 3, minus b2, that's negative 3, 0, times the sine of 3t. All that times c1 plus e to the 5t times, now the column vectors switch places. So negative 3, 0 is now in front of the cosine of 3t. And 1, 2 is in front of the sine of 3t. And because of what we needed to do with the conjugates and all of that in the preceding discussion, in front of the sine term, we have a plus. All of that second solution is times c2 using our superposition principle, and that's our solution.